All right, this is Mountain Building Lecture, Earth Science Lecture number 15, and we will begin with some vocabulary that you need to know for this subject. And this is, again, a subset of plate tectonics. Okay, we're going to start off with orogeny. Orogeny means it's a mountain building event. I'm going to repeat that one more time so you can get a chance to write it down. Orogeny is a mountain building event. Uplifting is the raising of large areas of rock due to a higher elevation. Uplifting is the raising of large areas of rock to a higher elevation. The subduction zone is an area where two tectonic plates come together and at least one is forced deep into the earth where it melts in the mantle. The subduction zone is an area where two plates come together and at least one is forced deep into the earth where it melts into the mantle. Thrusting is when blocks of rock are forced up onto and across the continental crust through the force of a continental collision. So this would be a convergent boundary. So this is when blocks of rock are forced up and onto and across a continental crust through the force of continental collision at a convergent boundary. A fault is a juncture between two blocks of rock. It can be small or large, and a fault is where movement occurs. A fault is a juncture between two blocks of rock. It can be small or large, and this is where movement occurs. And of course, you should know magma and lava by now. I go over it every single time, so you should be able to say it with me. Magma is molten rock under the ground, and lava is molten rock that's on the surface. Okay, so starting with mountain belts, if you were going to look at a decent map of the world, one that shows the topography, you would quickly recognize that mountains aren't randomly distributed and they don't occur as isolated features. So they occur in belts. They're in large bands across the planet, and you can see that they're also pretty linear. If you take a look at the Andes Mountains, you look at the Cordilleran Mountains, which are also called the Rockies in certain parts of it, you'll see they're almost in straight lines. So pretty interesting. If you strip the earth of its water, and that's something that the best maps also do, you'd have seen that most of the world's most impressive mountain belts occur beneath the surface of the ocean. We didn't even know these things existed until the 1940s when, during World War II, we started doing sonar surveys of the surface of the ocean floor. But now you should understand that these mountain belts are the result of plate tectonics. Okay, this should not be a shock to you at this point. Okay, so some of the major mountain belts that we're talking about. The most impressive mountain belts occur where the plates collide with one another, and the Cordilleran Mountains of western North America and the Andes of western South America are the result of oceanic continental plate collisions. The Himalayas are a result of continent-continent collision, which is the Indian and Asian continent tectonic plates, smashing into each other. Some transformed plate boundaries can also result in impressive mountains. Anyone in Southern California can tell you that the Sierra Nevadas are pretty darn impressive, and they are a transformed plate boundary there. Also, you see the same thing in New Zealand, which is the Tasmanian Mountains. They're also called the Southern Alps. Mid-oceanic ridges, like the Mid-Atlantic Ridge or the East Pacific Rise, as well as the divergent plate boundary in eastern Africa called the East African Rift, are all mountain belts that are as much the result of heat, so thermal expansion, as they are from deformation from continental collision or from plate collision. all in all, there are a lot of very impressive mountain belts on the surface of the Earth. By the way, just to remind you, many people call the Cordilleran Mountains the Rockies, but it isn't entirely correct. The Rocky Mountains are just one part of the range of Cordilleran Mountains. Other parts of the range include the Cascades in Washington State and Oregon, the Front Ranges of Alberta, and the coastal ranges of British Columbia, in addition to the Olympic Mountains in Washington State. Those are all part of the North American Cordillera. So you can call them the Rockies in Idaho, but in other areas it's not. Okay, so let's compare the Appalachians and the Cordilleran Mountains. The Cordilleran Mountains are tall. The highest mountains exceed 6,500 meters above sea level. That would include Mount McKinley in Alaska. The Cordilleran Mountains are also rugged, and you can see a picture here. This is the Teton Range right here. In contrast, the Appalachian Mountains are relatively short. Most are less than 2,000 meters in height, and they're rounded. They have gentle slopes. If you take a look at the mountains over here on the right from the Appalachian Range, you'll see that it's very, very smooth. And the difference here is the age. The rough, rugged ones, like the Cordilleran Mountains, are very young, and the Appalachians are extremely old. And so erosion has had a long time to work on those mountains and smooth out the curves and lower them down. Those that are rugged, like the Alps and the Cordilleran Mountains, are relatively young, and those that are not, like the Tasmans, the Urals, and the Appalachians, stopped growing hundreds of millions of years ago, and since that time they've been at the mercy of chemical and physical weathering. They've been eroding away and producing billions and billions of tons of sediment in the process. The real mystery isn't why some mountain belts are rugged, whereas others are not. The real mystery is why the mountains stopped growing 300 million years ago, like the southern Appalachians, or earlier, like the Urals over in Asia. They were formed about 500 million years ago. And it's amazing that even though they've stopped growing a long, long time ago and erosion has taken place, the amazing thing is that they have any kind of, shape to them above the ground at all anymore. You'd think that in that time they would have been worn away to nothing. They would have been, but there's an important mechanism at play called isostasy. And so that's an important one you'll need to know. And so that you're not confused on how to spell that, here it is. Okay, so let's consider the Appalachian Mountains for a few minutes. This mountain belt stretches from central Alabama all the way to the Newfoundland in East Canada. So if you look at the topography of mountains in the south, like Alabama and Georgia, with the north and Newfoundland, you'll see that the southern mountains are considerably more mountainous than their northern equivalents. The difference is due to age. The forces that produce the northern portion of the Appalachians ended about 500 million years ago, but the deformation in the south lasted until about 315 million years ago. The southern Appalachians have about another 185 million years before they will be reduced to a peneplain. And let me talk about peneplains here in a second. An example of a peneplain is Uluru. It's a great block of up-tilted sandstone that's in the middle of the Australian outback. Uluru used to be called Ayers Rock. This is the world's best developed peneplain. And Uluru itself is the best known monadnock. Peneplains are surfaces that have eroded to almost perfectly flat surface, and a monadnock is an isolated rocky remnant of erosion left standing above it. So peneplains are an old-fashioned concept. You won't see the word very much in your books or anywhere else. It was first put forth in 1889, and the idea was that landscapes evolved from young rugged form to end staging, which almost approximates a perfect plane. In most cases, this is irrelevant because the Earth's surface changes too much, which interrupts this process. But However, Uluru is a great example of it, and also Mount Monodoc, which is where the name comes from in southern New Hampshire, is an excellent example of it as well. So around the world, besides peneplains, you will see the remains of mountains occurring in different places. And you can recognize the remains of mountain belts that are a couple of billion years old, even though the mountain has not rested there for more than 1.5 billion years. Excuse me. Some of the rocks now exposed at the Earth's surface contain minerals or features suggesting that they originally formed well below the surface of the Earth, some more than 20 kilometers or more down. But the rocks have been moved to the surface of the Earth. And so you kind of wonder how all the other stuff around them could have been removed. This is an example here in this picture of the remains of a mountain that was found in the Transylvania region of Romania. Well, the reason that this stuff still exists, even though we have cases where the rest of it has eroded away, is called the continental roots. If you draw a cross section through a major mountain belt like the Cordillera, you'll find that the shape of the top of the mountains is reflected down below in the subsurface, and those are called the continental roots. And these roots are made of the same material that the mountains are, which is essentially continental crust. We usually picture the continental crust to be composed of granite, especially when you talk about plate tectonics and subduction. But remember that the ocean crust, which is basalt, is more dense than the continental crust, and it usually means that the ocean plate is subducted beneath the continental plate. Even though the continental crust is less dense than the oceanic crust, the rest of the lithosphere it's resting on, it's still pretty darn heavy. And so this is what causes the continental roots to form. The additional weight of these mountains causes the crust to depress downward. And so if you want to picture that, picture it with thinking about certain kinds of styrofoam. If you take one sheet of styrofoam, it's pretty low density. It's going to float on water. So the process of mountain building basically would add more styrofoam to it. And so the styrofoam builds up, builds up, builds up, and even though it's not very dense, it will still push down into the water. And that pushing down below the surface is equivalent to the continental roots. As weathering and erosion removes the tops, so it's taking off some of these styrofoam layers at the top, what happens is called bounce back, okay, or spring back. So it's kind of pop back up on top of the mantle. It's not as heavy, so it's not pushing it down as hard. And that rebound is called isostasy. The more the rebound, the deeper the rocks that become exposed to the surface of the Earth. So those ones I was talking about that could be 20 kilometers down into the subsurface, that was probably a very, very, very large mountain chain that has now popped back out to the surface. Once the roots have gone, isostasy can no longer continue. The mountains are finally reduced to these flat peneplains, and the process takes about, as far as we can tell, it takes about 500 million years to complete the process itself. Okay, so let's take a look at an example of something that's, fairly common that we're familiar with. We're going to talk about a young mountain range, the Himalayas. So you can take a look here at the satellite image where I'm pointing. You can see that the Himalayas, this big long range, it's almost a straight line. It straddles the borders of India, China, Pakistan, Tibet, Nepal, and a couple of other troubled countries in South Central Asia. This is the highest range on the planet. Mount Everest and K2 both exceed 9,500 meters above the surface of sea level, so that's like over 29,000 feet. They're very young mountain range. India really only started to collide with Asia near Tibet only about 40 million years ago. So the Himalayas are quite young. They're younger even than the Cordilleran Mountains here. The Cordilleran Mountains started around 150 million years ago, and the Appalachians around 500 million years ago. So basically the Himalayas are babies when it comes to terms of age of this range. Okay, so we've got these plates colliding, the Eurasian plate and the Indian plate. And the most prominent feature of the Himalayas is this line of junction between the two plates. The continental crust is more than doubled in absolute thickness. It's more than 100 kilometers thick above the mantle. And this junction line is called a suture line. It marks the place where India is wedged under Asia. It's extremely hard to subduct granite under granite. So the plates are now firmly stuck together. So the Indian plate south of India is still moving north, but the front end of the plate that's stuck under Tibet isn't moving anymore. So it kind of makes you wonder where the new subduction zone is going to develop in India, and it eventually will. I have no idea when, but it eventually will. So taking a look at the Himalayas a little bit more carefully, you'll see all three types of rocks there. The igneous rocks are going to be widely distributed throughout the mountain belt. They will vary from granite, which is often found as intrusive felsic rocks and plutons within the crust. And you can take a look at this granite intrusion right here in this picture. And it will also include rhyolite, which is an extrusive felsic rock from composite volcanoes on the crust. You'll see diorite and andesite, which are intermediate rocks, pegmatite, cyanites, tuffs, volcanic ash, etc., etc., etc. Even basalt and gabbro can occur in some parts of the mountain belt, but mostly you're going to see granite and you're going to see rhyolite in the Himalayas. The sedimentary rocks are also found very well distributed across the body of the Himalayas. There are all sorts of Mesozoic and older sedimentary rocks that were there before the Himalayas began to form, and then there are all the sedimentary rocks and sediment that form through the erosion of the mountains themselves. So you're going to see arkose and breccia in the mountains in alluvial fans, sedimentary rocks like conglomerate in the riverbeds, red shale in the floodplains, quartz arenite in the beaches, and more distal areas of the sedimentary wedges that pass from the mountains to the adjacent plains. There are even shallow marine sediments deposited along both sides of the mountain belt, because before the Indian plate hit the Eurasian plate and started to shove underneath it and then get stuck, before that happened there was a sea there, and then they got pushed up. So you're going to see marine fossils and sediments there too. And if you take a look at this little cairn of rocks here, those are all sedimentary rocks that you can see in the foreground. Finally, metamorphism also occurs in the Himalayas. Convergent plate boundaries are where regional metamorphism occurs. Don't forget that, regional. It's in that area. Both heat and pressure induce the metamorphic changes in this tectonic area. The grade is highly variable. The closer you are to the suture line, the greater the pressure it's going to be. The deeper you go, the higher the temperature. So you find every single metamorphic rock possible in the Himalayas, because this contact metamorphism also occurs near the plutons. So you've got literally every kind of metamorphic rock in the Himalayas. And so it's pretty interesting. Okay, so enough with the Himalayas. I want to talk about one type of fault that we see in mountain building fairly frequently, and that's thrust faults. When the rocks become permanently deformed, they'll either break or they'll bend. And breakage usually occurs along the leading edges of both sides of the mountain belt. So in the Himalayas, this has resulted in a series of low-angle reverse faults, which are called thrust faults. They radiate away from the suture line itself. Folding is more common closer to the suture line because of the higher pressure and temperatures there where this metamorphism is occurring. Right along the suture line, the pressure and temperature is so extreme that the rocks literally get metamorphosed past the point of just bending. And so that's actually where you get the thrust faults, where it's actually shifting the whole set on top of one another. Okay, so that is it for mountain building. Do not expect too much on the exam for mountain building. You will see a few questions, but it's not going to be deep detail. Make sure that you know that orogeny is associated with it, isostasy is also associated with it, but pretty much, you know, be able to understand that the smoother the mountain range is, the older it is. The more jaggedy, the taller, it's younger. Those are the big key concepts I want you to get into this lecture. So, go ahead and try the practice quiz. Good luck, and I will see you after winter break.